Many of you remember doing science fair projects as you were younger, and a lot of times we would do a science project a lot like this, where we would have a growth of a plant over time. So this is the number of weeks, and this would be the number of inches. And if you did your science fair project like you were supposed to, you actually got the tape measure out and you measured how tall each one of the plants were after the certain number of weeks. And you may have gotten some data that looked a lot like this. So after the first week, there it is, less than an inch. 2 weeks, it's up there a little below 2 inches, and then it's continuing to grow. Although if I were to graph this out and plot it, it would look like it was staggered. But we know plants don't really grow in those staggered things like that. It would be much more of a nice, easy curve or straight line. This allows us to take experimental data through linear regression, and we're going to make data that isn't a straight line into a straight line. There's a couple reasons we do that. One, we want to be able to show the function that over time of weeks it is getting taller. It's not shrinking, and time's not running backwards. So it's going to do so. Although it is a linear regression, because we're losing data. The regression part tells you that, hey, I don't have all the data that I would normally have. I'm actually losing some data. I can't go back. So it's regressing. So when I look at this linear regression, I'm going back to the best straight line that I can come up with. If I put that straight line in here and said, well, somewhere it would be somewhere like this here, this is where it would be, and that's called a line of best fit. That's the best location I could put it in there. Now there's a problem with this, and that is that each one of you, as you do this on your own, may come up with a little bit different of a line. See, I could just as easily have made a line that looked like this here, or a line that looked like this here, and it still would have been the same overall linear regression, although it varies just a little bit. And the more data that I put in there, the more variation, or the less variation I would get. But data is not perfect. And because when we experiment with data, it's not perfect, we're going to have some things that don't work out nicely every time. So what we're going to do on this is we're going to take that line of best fit. I'm going to take that center one, it's the one I like the best, and I'm going to find the equation of the line that best represents that data. If you remember from your previous lessons, y equals mx plus b is the easiest format of using y-intercept of the equation of a line. I remember that slope is m. M is the value here, and that's what that slope is going to stand for. And slope is rise over run. It's the change in y over the change in x. So how would I find that? Well, I could say y2 minus y1 over x2 minus x1. But that leads to another problem. I've got to have some points. So I look at this and I say, you know what? It looks like it's crossing at about 2, 2. That's a good point there. And then if I came over here, it looks like it's crossing at about 5, 4. And now I'm not just randomly picking points. I'm trying to see about best where that lands, and that looks about right there, and looks about right there. And that's why it's in a regression. It's not perfect. So once I get to this point, I go ahead and use my formula. Well, y1 is 4, and so 4 minus 2 over 5 minus 2, and I'm going to end up with a slope of 2 over 3. Now, this works out nicely for us because this is a positive slope. Remember, going left to right, uphill is positive. So it is a positive slope. That's good. Our data represents appropriately here. And I remember that that is my m. So now I'm going to plug that into my formula, and I'm going to say, okay, y equals 2/3 of x plus b. But I'm still missing something for this line, and that would be the value of b. Remember what b stands for. B stands for the y-intercept, and I don't have a good y-intercept here. I would have to extend my graph and take a guess if I was doing it that way. But thankfully, I don't have to. I can take either one of my points and plug this in. So y is 2 equals 2 over 3 times 2 plus b. 2 times 2 is 4, so I'm going to say 2 equals 4 over 3 plus b. And then I'm going to subtract that from both sides. 2 minus 4 over 3 equals b. I'm not quite done. I need a common denominator, but that's pretty easy to do. My common denominator is 3. 3 times 2 is 6. That's going to make this a 6 over 3. 6 minus 4 is 2, and that gives me a 2/3 equals b. Now, this isn't going to work out every time where you end up with a problem like this, where it ends up being the slope and the y-intercept happen to be the same. But on this problem here, it did work out that way, and 2/3 is my slope, and also happens to be my y-intercept. This is how you figure out linear regression. It doesn't really matter if it's a positive or negative slope, depending on the data it represents. And of course, there could be something that data was not perfect on. So I could have one of these that is so spread out that the linear regression is not very good. It's not a strong correlation. Or I could have it very close together like my data is here, where I'm not going to have much variation in the answer. For testing and and quizzes and homework, when you're doing your own work, we're looking for something that's close to that slope, because depending on where you put these points, it's going to have a different slope. So where you put the line of best fit and where that problem happens to be may be different at this point in your career.